the class. Today we continue building our datapaths, and also we go to controller today. Before that, if you have any questions or comments, please let me know, or we can go to reflections and look at the reflections. Any questions? Are you following today up to now? Yes, please.
Excuse me, but when will we get our midterm grades back?
They are marking. They are being marked now.
Okay,
hopefully, maybe next week.
next week, thank you.
It's too much. We are trying. Yeah. Any questions? Yeah. Database. So as you have seen, we try to implement a database and later a controller for a single cycle processor for a limited set of instructions, not the whole instruction set, which would be similar almost. The concept would be similar, but for the sake of simplicity, we just selected a set and then we try to implement them. So let's go to reflections, see what you have written here. Okay, so the first one was asking about write the instructions from the limited set, not from the whole instruction set, which will update a register. Which instructions update the register? Then explain what would the different source values for the register to be updated, and which control signal selects the correct source. And also explain about write control system. Okay. So there are different questions. Which instruction updates the register? What would be the source values? And how do we select which source writes the registers, update the registers? So maybe Tony is the first, so we start with Tony. Tony is here? No? Tony is not. Well, let's go to the next one. Ishan is here? No, Ishan. Zimu? Yeah, absent. Akachukwu. Yeah? No? 3, 4, 5, 6, 9, 10, 13, 17. We have 20 people here. We have 33 posts here. So I hope we can find a common students here. Jayashan? No. Laser? Okay, Laser, good. You are a lifesaver. Thank you. Okay.
We'll see about that.
Okay. To update the register, we take the data that goes into the register alongside the control signal, right, in order to update. Okay. Furthermore, it has to be updated at the clock date of the update to take effect. We also need to read two data. You shouldn't go to this detail. This is not required for the updating the register, okay? The right signal control. But you haven't talked about the instructions, yeah?
That's correct.
Which instructions do you think that updates the register? Just name one or two.
Add or sub.
Add. If you have add, for example, add T0, T1, T2, then it updates T0. Yeah, that's good. What else?
Well said, sub.
Yeah, add, sub, or, and. These are arithmetic or logic operations, okay? A kind of instruction and another kind of instructions which updates the register. Any idea?
Word.
Load, yeah. So if we have two instructions, let's see, for example, if K1 is different, so no. Why don't we have that? Are all the arithmetic operations and all logic operations, that's it? Mason. No load. Instructions, not that one. Then Showin. Showin. Yeah. Add sub load were perfect. So it's complete, I guess. Add sub and maybe we have nor ISO, but it's not in our limited set. No, yes, that's right. So for our set, we have picked up this. Very good, Shahi. So these are updated. Very good. So Lazar, you mentioned about the control, also the control, but you haven't mentioned about the name of the control signal. What about Shahin? Adds up through the register file and ALU to process two input registers. Very good. The result will be passed back to the register file. The control unit will send the correct signals to allow ALU output. And what would be the name? I guess we haven't talked about it, but I guess we talked. That's good. Load will pass the base address from the register file to the ILU, okay, as well as an offset, okay. And then these values will be added and go to the data memory. The data from the provided address will then be loaded and written to the destination. So we have two sources of updating a register, load and ALU operations. A store doesn't update a register, it updates the memory. Very good. Okay, good. Let me see, what was the name of the control signal? We talked about it here, I guess. Here. Yeah, we talked about it here. Which multiplexer am I talking about right now? The multiplexer which selects which data to be written to the register file. The register file, the data which would be written to register file would be this. So where this data comes from, it comes from this multiplexer. And as you see, this multiplexer has two sources, two inputs. One input is coming from the data memory when we have a load instructions. The data coming from here to this multiplexer. The other input of this multiplexer coming from ALU, this one. So two sources for updating the register. And what controls this signal? This signal selects which one of these inputs go to register file. And that would be coming from the control signal. We didn't have the name. I guess we did. We didn't. Maybe we didn't. Okay, so, but it's coming from control signal, and the name, there would be a name here, which I was thinking that we have talked about it. No? Okay, we will talk about it today. Okay. So that was the first reflection. The next one would be this. What this diagram shows, there is a sequential, synchronous, yes.
Oh, sorry, just in regards to the first question, what instructions were like in the limited set? Like what was defined?
Please repeat again.
What instructions were in the limited set? Like what's defined as a limited set?
At the beginning of the datapaths, I've told you, it is add, maybe I have the slide, I don't have. Let me see if I do have a slide here. Yeah, here. Simple subset. Memory reference, load and store, arithmetic, logical, add, sub, and, or SLT, and control transfer, branch, and jump. That's it. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9 instructions out of the whole set. we just implement these, and with this you get the idea of how to design a processor. So the question says, what is this diagram and what determines the maximum clock frequency? Okay, let's see, what did you write? Hopefully somebody pick up. Christian, here? Oh, okay, yeah, I forgot. Christian. Okay. So that diagram, what is that and how clock frequency is determined? This diagram represents the performance of an instruction throughout the interval of a clock cycle. As shown above, the instruction begins with a certain state element, performs a combinational logic operation, and then returns as an updated new state elements. Okay. We also notice that throughout this computation, the changing of states and performance of certain operations are dependent on the timing of the clock cycle. Actually, they are not dependent on the clock cycle. They are dependent on the operations that we are doing, like the gates that we have and or combinational logic. But the clock cycle will be determined based on the delay and the time that we have. So maybe you meant that, I guess, but when we say it's dependent on that, we should be more precise. Throughout this computation, the changing was okay, such as when the clock is set to actify. Judging by the layout of the diagram and the timing of the clock cycle, this instruction set appears to be positive edge triggered, also known as rising edge when we overpass them. Rising edge trigger occurs, okay, furthermore, set operation falling edge. I am now looking for the critical path. Also, this is a very basic diagram. It could be possible that the combinational logic circuit depends on the state of the clock to complete its full set of commands. The first half performs combination, then awaits for, no. The whole clock cycle is for the combinational logic to perform, not just the first half, the whole clock cycle. But at the rising edge of the clocks, this one, and then the next one, this cycle time will be the amounts that the combinational logic needs to perform. So the whole thing. Translating this further, the maximum, okay, here. The maximum amount of cycles for the maximum clock frequency represent how the most amount of instruction that, it was not good, Christian. For the measured maximum amount of cycles, for example, let's say the clock cycle given is the maximum, then we can say that the maximum frequency is approximately 1.5 seconds. No, it was not good, or I don't understand. This part, I didn't understand. Do you have any comment?
I just meant more in the sense, like, looking at the picture that the maximum frequency is that amount of cycles, like in the picture that you described.
This picture, this diagram only shows that the combinational logic that we have in between two rising edges is doing something, and it takes time. For sure, the combinational logic takes time. We have gates, we have delays, we have wires, they have to move, the electrons need to move. We have delays. So the delay, the time which this logic takes to perform, it should be less than the clock cycle. Because if it is not less than the clock cycle, then the logic is still performing something, and it is not perform the output here, and then the next clock comes. When the next clock comes and the operations has not finished, we get wrong address, wrong results, and it's not good. Everything should be finished before the next clock cycle. So when the clock comes, everything is ready, and we move to the next state, to the next clock. Okay? And I've told you last time, there might be not just one pass. For example, we have and or here going and preparing some of. We have another pass with another set of combinational logic. We have another pass. There are different passes. It is not just only one pass. And the longest path should be considered because we want everything to be ready. So among all those combinational logic paths that we have, we should consider the longest one. Because if it is ready, then everything else would be ready because they are less than that, they are shorter. So we should consider the longest path. And that longest path would be the critical path. And that would determine the clock frequency. Okay? Yeah? Okay. So where were we? Okay, we were here. We have started building our data paths in more detail. The first one was instruction memory and the fetch. Then we went to R format instructions, and we have looked the data paths for the first part of execution because it will continue. But the first part would be in when we have a R format instructions like and. We have we have and S0, S1, S2. This is an instruction, a R format instruction. In R format instruction, we have opcode and function code, each one 6 bits. Then we have RS, RT, RD, source, the other source, and the destination. And then we have shift amount, which is 0 now. So this is source. Source here is S1. So we have S1 here. And this would be the next source, it would be S2. So S2 is here. And this would be the destination, which here is S0. So we have an instruction. The instruction coming out of instruction memory, which we have seen in the previous slide. So the instruction is 32 bits. These 5 bits, which is the source, comes here. The next 5 bits, which is the next source register, coming here. We have 2 5-bit coming from the instruction. These 2 will determine the read registers that we want. What registers we would like to read? We would like to read S1 and S2. So the address of S1 and the address of S2 coming from the instruction. And they go to the register file. When we have address here, the data, the content of these registers will appear here. Now we have the value of S1 here and the value of S2 here. Okay? Now these go to ALU. And what was the operation? The operation was AND. So we somehow, the controller should tell ALU from here with this signal, ALU operation, that ALU, you should perform AND now. AND with these 2 values, and the results coming here. So this is an example of R format arithmetic or logic operation. It's not finished yet because when the value, the result coming out of here, it should be written to S0. So we have something from here writing, coming back to the register file, and we have the address of S0 here, and the register file will get updated based on the value that we got from the ALU. Okay? Useful. Do you want me to repeat again? Just very fast. To address, to read register address comes from the instructions. The value gets ready here. They go to ALU, the result will be calculated and written again on the next register. Okay, so this is our format. The other instructions that we talked also in the reflection part is load. And store is also another instruction that doesn't update the register. The store updates the memory, load updates the register. Load reads data from the memory, updates the register. Store reads data from the register, updates the memory. Okay. So again, we need register operands because, for example, for a load, what do we have for a load? We have load, a register, for example, A0 with offset and base. Some offset, like say 10, this is the offset, and a base address, and for example, S0. So this is a load, a typical load instruction. As you could see, we have a load instruction was, how was the format? We had 6 bits of opcode. Then we have 5 bits RS. And then we had 5 bits RT. And then we had 16-bit value, immediate value of offset. Does this make sense? You are looking some kind of new materials, and we have talked about this before. Okay, so here A0 is the destination, so RT would be A0. 10 is the offset, so this 16-bit value would be 10. Signed value, 10. So here is plus 10. We could have, for example, minus 10. Let me put minus 10, that would be better. Minus 10. Minus 10 goes to here, A0 RT, and we have S0 as the base. So S0 is here. When the instruction comes here, we have RS. So if I write register file here, we have RS. It's very close to here. Okay. This is the read register data. So we have RS coming here, which in our case is S0. So address of S0 comes here. As soon as address comes here, register file prepares the data value here. So we have the value of S0 here. The value of S0 is here. And also in the instruction, we had these 16 bits. So this 16 bit also coming from the instruction, they go this value, S0, and this immediate value go to the ALU. And they will be summed together. This, what is this? What is this calculated? Offset plus base. What is this? Where should This go. Help, please help. Huh?
Should it go into A0?
No, A0 is the destination register. After we load from the memory, that value goes to A0. But first we need to load from memory. What is this? What is this that I calculated? I brought S0 from register file. S0 here, S0. S0 from register file. And minus 10 from the instruction. And I am adding them together. What do I find?
The index of the source register. It's like the value at the 10th index.
The source register, no, the source register is S0. And we get it, and then we add it to minus 10. What do we get? Yeah?
Like the address you want to access from
The address that we want to load from the memory. So this would be the address, and this goes here. This is the address of the memory that we want to load from that. This instruction, look at this instruction again. Load word A0 with 10 plus S0. 10 and S0 determines the address of the memory that we would like to load from it. And they need to be added together. How do we add them together? Use ALU, the ALU that we had, and we have seen it in the previous slide. This is the ALU. So the source S0, the base address comes from here. Then the immediate value comes from here and goes there. And if you remember, which I am almost sure that you don't, there was a multiplexer here saying that which value should go to the ALU, either the immediate value or the value that we have read from the register file. Here, in the load instruction, we get the immediate value, we get the first offset, the source register for the base address, they add up together, and the result will be here. This result goes to address. This result, this is the result. This is here, this is the ILU. So the result of ILU goes to the address of the memory. We have address, we have load. So we need to read data. We have address now in place. Then we activate mem-read control signal. And the memory starts working and the data coming out of here. So where does this data should go? So we read from memory. Where should it go? Look at the instruction. Load word A0 with the address. Where should it go? The value that we have read from the memory. No? Yeah? Yeah.
it goes to A0?
Yeah, it should go to the register file and updates A0. Yeah, the value goes there. Okay, now we go to branch instruction. And from the set that we have selected, we just use branch on equal. You remember, there are two branch instructions, branch on equal, branch on not equal. We just look at the branch on equal. Not the branch not equal would be similar. So what would be the instruction for branch on equal? Let me write it here. Branch on equal, two registers like V0, V1. I just put different registers so you know they are just examples. It's not something that branch on equal V0 with V1 and then go to a label, a place, a target address, somewhere that we want to jump there in the branch. So this is the branch instruction. Again, if you remember, the branch instruction has an I format. The format of the branch instruction is I format. So again, this would be something like that. We have 6 bits of opcode for branch. Then we have 5 bits of RS, which here would be V0. In our example would be V0. We have 5 bits of RT. In our case, in our example would be V1. And then we have 16 bits of target address. Actually, the relative target, these 16 bits will be added to PC and would be the new target address after multiplying by 4. If you remember, we multiply this by 4 and then we add this to PC. Okay, again, the same thing that we have taught in the previous instructions. We have 2 value coming from the register files. Again, we have the register file, the instruction coming from the instruction memory, 5 bit goes here, 5 bit goes here, which would be V0 and V1 in our case. V0 and V1 address coming here. Then we have read data here. So the value of V0 would be here, the value of V1 would be here. Then they go to the ALU again. ALU. They go to ALU. What kind of operation ALU perform on these 2 values for this instruction? Branch unequal V0 and V1 and jump somewhere. What kind of operation do we have to do on V0 and V1? Subtract, because we want to compare. Yeah, subtract. Perfect. You're just helping me. So we do subtract. And when we do subtract, we are just concerned about the result would be 0 or not, because if they are equal, we are looking for the equal, branch unequal. If they are equal, the result would be 0. If they are not equal, the result would not be 0. So we are just concerned about the, where is that? Oh, maybe in the next slide. We are just concerned about the 0 value. Then this 0 value comes out of ALU and goes to some place to control the next PC. The next PC would be either the regular PC, I mean PC plus 4, or PC plus 4 plus this address, this immediate value. Okay, so let's read through it and then look at the diagram. So what will we do? We use ALU to subtract and then bring and find the 0 output. We also need to calculate the target address, sign extending this 16-bit value, and then multiply by 4, shifting 2 bits left, and then add this to PC plus 4. So here is the target address. The PC plus 4 was already there. You remember we had a PC plus 4 always ready there. So we just add them together. Look at that. So in our case, V0, the address coming from instruction, and V1, the value coming out of here, they are subtracted, and the 0 output comes out of here. And this 0 output should control the multiplexer. Do I have it next slide? No, I have it later. We have a multiplexer here, which one is coming from here, the other is coming from, sorry. Yes, the other, sorry, this is the control. This 0 this 0 output controls this multiplexer. Which address should we go to the next PC? One address is PC plus 4. The other address is this one, the immediate value read from the instructions. Shift left by 2 means multiply by 4, plus PC4, PC plus 4, this is the branch target. The other one is this. So this multiplexer has two inputs, PC plus 4 and target address. Depending on the value of this 0, one of them goes for the next PC. This is PC here. So the next PC would be one of these two. So this is branch. So we have seen add, and an R format arithmetic or logic operation. We have seen load. Oh, we haven't seen a store. It's not bad if we have a look at a store also. And we have also seen the branch. For the store, whatever we talked about finding the address is the same. We have offset and base. When we find the address, then also we have the data. The data, this register, where was the register, the offset? This register for a store. This register, this is address. Where is the data? Data is this one. In a store, we write a store, a register like T0 and an address. So this T0 coming from the register file goes here to write data. We have the data, we have the address, then the control of memwrite comes. When the control comes, this data is written into the memory at this address. So for the store is also the same. Okay, this was the branch instructions. Now you know the different parts of data paths. Let's put them all together. And you see, for this, we would like to have a single cycle processor. What do we mean by single cycle? We mean that with one clock cycle, everything should be done for the execution of the instruction. The instruction could be add, T0, T1, T2, could be load T0, 5, T2, could be a store, T0, 10, T2, and branch, it could be branch. Which either of these instructions should be executed in one clock cycle. And you know, they are different, and they have different times to perform. So we should find out which one would be the longest, and our clock is determined by the critical path, the longest path for executing the instruction. So everything should be executed in one clock cycle. Fetching the instruction, going to register file, calculating ALU, putting in the data memory, and writing back to the register file. These things that we are ever doing. Fetching the instruction, coming out of instruction memory, going to register file, getting the registers and the immediate values that we want, then calculating whatever we need, then going to data memory for load to get the value, or for a store to store the value. And if it is a load, for the last operation, we need that value to be updated, to go to the register file. All of these things should be done in one clock cycle. So everything should be there. I mean, we need a different component for ALU, a different component for instruction memory, a different for the data memory, a different component for register file. We cannot share this hardware. Everything should have an independent hardware for itself. Therefore, we need separate instruction and data memory, because you will get, later that the processors have one memory both for instruction and data. But here we are saying that no, it's not possible, because we would like them all to be done in one clock cycle. If you want to have a single cycle processor, you need to separate instruction memory from data memory. Later, when we talk about pipelining and having them in different clock cycles, then that's okay. We could have one memory, and when we want to fetch, we get it from the memory, fetch it. When we want to load or store, again, we use that memory to load and store it. Each data path element can only do one function at a time, because it should be done in one clock cycle. Instruction and data memory should be separate. We need multiplexers to direct different data to different locations. And this, again, going to see to the R-type or load store data path. It's not complete yet, but more complete compared to before. So the instruction coming from the instruction, the fetch operation, and if it is R format, arithmetic, we have two source operands. Both of them have value here. These value coming to ALU, calculated, and that value will be written back to the register file at T0, T1, T2. T1, T2 coming here, added, this value will be written back to T0. This is R format. Load, instruction coming, the register, load. The register, read register would be the base address coming here. The immediate value from the instruction comes here, sign extended, and multiplied by 4, which, multiplied by 4 is for branch. Sign extended, then they are added together. These two added together. This value is the address that we want to load from memory. The memory starts loading, and when the data comes, the data goes to register file and updates the register. If it is a store, again, the first source register coming here, which would be the base address, the immediate value coming here, sign extended, coming to ALU. They are added together. The address is calculated. The address comes to data memory, and also we have data. The other register is the data here. So we have this coming here, and this. Oh, we didn't have the. Okay, here. This goes to data memory, and this data is written to this address with a memWrite control. So this is a store. Again, I will show you this. When you have this register, the value of this register appears here. This goes for the right data of the data memory. So it is R-type, load, store, data path, without the instruction. If the instruction was also in this slide, what would be better, which I have it later. Again, look at the blue texts. These blue texts are the control signals. For example, here, you have ALU source. This ALU source says which source, either coming from the register for the R format instructions, or the sign extend value, immediate value, coming from the I format instructions should go to ALU for the second operand. The first operand is always this. It's good. The first operand always goes to ALU. But the second operand, it either comes from a register or coming from an immediate value. This is the ALU source. This control signal says which ALU operation should be done: add, subtract, and, or, these things that we had. I guess that's it. Maybe. I have to look at the instruction, the set of instructions that we have picked up. So add, subtract, and, or. This will tell ALU which operation ALU should perform on these two operands. Here we have memwrite. When we have a store, this will be activated and stores on them. Here we have memread. When we have load instruction, this will be activated. Here we have mem2reg. Mem2reg selects what should be updated in register file. It is either a value which is read for a load instruction from the memory, or it is a value calculated by ALU from an R format arithmetic operation. So it has two sources, either from the memory or from the ALU, and this will select which one should be go to register file. What else do we have? We talked about ALU source, ALU operation, memwrite, mem2reg, memread. Yeah, that's here. Read-write. Read-write will be activated when we want to update a register file, either in an R format instruction, which we need the value calculated by ALU to be updated in the register file, or a load instruction. With these two instructions, read-write will be activated. So you see, these control signals will define what should be done in this data path. The data path performs the operations. These control signals determine what should go where. This is full data path now. It's still not complete because from the set that we have selected, we had also jump. We haven't talked about jump yet. We had talked about R format, and then branch, and then immediate arithmetic operations, and also we talked about load and store. This is almost complete. You see, for a branch instruction, which we didn't have it at the previous slide, for a branch instruction, the operands coming from here, they go to ALU to compare it. The results. This is not correct. The result, the 0, goes somewhere which selects this. We call it PC source here. This 0 selects which address should go to the PC. Okay, for branch, 2 operands, 2 registers compared to each other. The result of the compare coming here, it is either PC plus 4, this is PC plus 4, or PC plus 4 plus the value which is multiplied by 4. This is the target address of the branch. If the branch is taken, this target address will go to PC. If the branch is not taken, this address goes to the PC. And this is the branch. I guess we have talked about all the instructions. And here also you could see the PC, which is a very important component here, and it determines which instruction should be, which instruction memory should be fetched from, the address of the next instruction to be fetched from. And this is instruction memory. For the instruction memory, as you could see, we didn't need to put some kind of control for read or write, because in instruction memory, we don't write, we just read. So every time, in every clock cycles, the address coming from PC and the value should be here, the reading from the memory should be here, so there is no need for a separate control. It always works, it always reads, so that's it. It should be active all the times, and it should always prepare the data for us. So there is no control here, just address, just data, just address, just instruction coming out of the. What else do we have here? Okay, nothing. Good. So this is the full data path. ALU, I told you, is used for load store because we want to add the base address with offset, so we need to add. So ALU is used for that. And with the function add. ALU works as an adder at this instruction. We have branch. Again, with branch, we use ALU to compare to operands. So again, we use ALU, but here the operation would be subtract. Subtract. We have, we use ALU, this is very obvious, the most obvious operation of ALU. Two registers coming, they will be, some operations will be done on them, add, subtract, and or, and the result will be repeat. Again, it depends on the function field, because in our format, if you remember, the opcode was 0. The function code shows which function add, subtract should be done. Let me bring it for you, Joe. You need more reminders. We had here, where is the reference? I lost my green sheet, the green sheet that I had, the reference. So I have to use this. Okay. So I open in Adobe. Oh, what's happening? Okay, good. So look at this. Where is the full screen display? Full screen control. Okay. If you look at these here, then for, let's say, add instruction. Add instruction, the opcode is 0, but the function code determines what is that, which is 20. So in our format instructions, like add unsigned, which we don't talk about it right now in our datapaths, and also nor, again, we don't talk about it, but or, we have SLT. These instructions, as you could see, all of them, the opcode is 0, the function code determines what should be done. So remember that we have a function code from here. So in our type, we use the function code. Let's go to branch again. For branch, the function of ALU is subtract. When do we find out? From the instruction. Branch. Where is branch? Branch. Do you see branch here? Branch unequal. Branch unequal is 4 hex. The opcode is 4 hex. When we have opcode 4, it means that we have a branch, and it means that the ALU should perform a subtract. Here, subtract. For load and store also, there are opcodes for them. Load. For load, what do we have for load? Load word. Load word, we have 23 hex. When we have 23 hex, it means that we have a load, so we need ALU to calculate the address, and the ALU should perform add, an addition, and also a store. A store is 2B. A store is 2B. This is a store 2B. What functions the ALU does? And, or, add, subtract, set on less than, and nor. These are the functions that ALU should perform. And here, so it has less than 16 functions, which we don't have it all here because we just picked a selected set. We need only 4 bits for ALU control. The 4 bits selects one of the 16 operations that ALU should perform. For us, it is 1, 2, 3, 4, 5, 6 operations. And these are the control signals. If it is 0, 0, 0, 0, 0, the data paths based on the instruction, opcode and function. The data paths based on these two generates 0, 0, 0, 0 for ALU. And ALU finds out that, okay, this is an AND. When we have 0001, we have an OR. When we have 0010, we have an ADD, and so on. Okay? So ALU control is a 4-bit number, determines the operation of ALU. Okay, if you look at here, okay, 2-bit ALU op derived from opcode, because remember, for branch, load, store, we have opcode. So from the opcode, we could find the ALU operation. But for our format instructions, we had opcode as 0, and we had the function code. So if you look at here, for branch and load store, we only have add and subtract. Add and subtract. So add and subtract will generate 1, 0 for ALU control at the least significant bits. So these 2 bits coming from the opcode. 2-bit ALU derived from opcode, okay? So if it is 0, 0, the ALU operation, it is load and it adds. If it is store, again, it is 0, 0 because it should add, and this adds. If it is branch, it is 0, 1, then it is subtract. But if it is R-type, then we have to look at the function code also. Based on the function code that we have for different operations, add, subtract, and or set less than, we build our ALU control. So based on opcode and function code, we generate these 4 bits. These 4 bits tells ALU what to perform. So again, let's look at the instruction. Control signals derived from instruction. It is either R-type, it is either load store, it is either branch. If it is R-type, all of them, opcode is here. The instruction set is very regular. All of them are 32-bit wide, and all of them have opcode, 6-bit opcode at the beginning. So it's very regular. So opcode coming out just from the instruction. Then we have first register operand. So in all of the instructions, we do have this. So and they always use for the read of from register file. But the second operand sometimes is for reading from that, sometimes is for, let's say, either destination to be written on, for example, in a load instruction. This is the target, the destination register that we put the value there. So they are read except for the load. This is read, because in branch you read these two and then compare it. In R-type you read these two and do some operation, but in load you read this one, calculate the address, and the data coming from the memory, you store it in this register. In a store also, you read this one, calculate the address. You read this one, this is the data which should be stored in the memory, and then you store. So you see these 5 bits very regular again, and the first one always read, and this is why you have seen, do I have it here? Oh yeah, and this is why you have seen the first 5 bits always go here for the read register. So everything. But the read register, second read register, it's not always used. For the load, this part should also go for the write register. The RT is the R register. Okay. So again, these are reads, these are write, this for load is write, this is write register for the R format instructions, and these are the immediate values which should be sign extended. For branch, it is sign extended and then multiplied by 4. For load store, it is sign extended and added to the base address. Everything is clear? You see how different parts of the instruction acts something in our data paths, has some kind of effect in our data paths. And they are very regular, it's good. You haven't seen other processors which are very complex and they are not as regular as the MIPS. So MIPS is one of the best processors that should be taught, and that's why we are talking about MIPS, not other processors. And that's why I wanted you to just have some kind of hand-on in lab for the MIPS. So we will talk about lab also later. So this is the data path, the whole data path you could see. The only thing is missing is jump. We will talk about jump later. Everything is there. Branch, load, store, ALU operations, everything is there. So here you see the one that we didn't have it in the previous slide. The result of the branch compare, this 0, comes from here. And if the instruction is also branch, which is determined by the opcode, then this will select the multiplexer that selects this address, target address, if the branch is taken. And if the instruction is branch, then this is taken for the next PC. We haven't seen this part in the previous slide. Other than that, we have seen everything else. Yeah. Any questions? Look at this for 30 seconds and ask. See if there is any kind of part that I need to explain more. Look at that. You should know every single detail of this. What is this MIPS? What is this multiplexer? what is this control signal, where does it come from, what does it select. You should know every detail of this datapath. A very simple datapath because we just selected a set of the instructions, not the whole thing, but it will give you the idea of a datapath and controller. Okay? These are the control signals which you can see. For example, reg destination. Where is that? Reg destination is here. Reg destination selects the multiplexer to say which value should go to register file and update the register. It is coming either from load or coming from ALU output. One of these two coming from here. Oh, no. This is, this is reg destination. The reg destination is, what does it do? Instruction. Okay, sometimes, if you remember, no, that was okay, yeah? Let me look here. This is what I am saying, that you should know every detail of that. This multiplexer selects between RT as one part and RD, the other part. RT was the destination in load instructions, RT, and RD was the destination in R format instructions. So we have to select which one of them goes for the address of the right registers. Yeah? So this is, for example, reg destination. Another one. For example, memread. Memread controls when data memory should read, when we have a load instruction. Memwrite is for store instructions and tells memory to store something in it. Branch means that the instruction is branch, so we should be careful about the next PC. The next PC is either PC+4 or the target address. So when we have a branch and when we have a taken branch, then the instruction, the PC gets from here. But otherwise, if it is not a branch, or if it is branch not taken, then the next PC would be PC+4. PC+4, this one. ALU operation, it was a 4-bit value, as ALU operation was 2-bit value coming from the instructions, and it will be combined with function code, and it has a 4-bit value for ALU control. ALU source. ALU source, for the first operand, we have always the register. But for the second one, for R format instructions, we have read, we have register 2. For I format instructions, we have immediate for ALU source. That's it, I guess. Yeah, that's it. If you look at here, it says there, register when it is active, what it does, what it selects, and when it is not active, what is it selected. And based on these things, based on the instruction, the destination, all of the control signals will be calculated. For example, if we have R format instruction, let's coming back to R format and do it together. R format instructions. When we have R format instruction, what would be the select for this multiplexer. I show you. I want to, for an R format, what I'm going to do is to find these control signals for an R format instruction. For an R format instruction, the first control signal is regdist here. It selects either from RT or RD. In R format, the operand is always RT. So this should be selected for R format values. So this is 0. The multiplexer has two inputs, 0 and 1. When we put the signal 0 here, it means that the multiplexer selects this. So let's see if, no, this is, sorry, this is the right register. The right register is RD. When we put 1, this will be selected. For the load, we put 0, so this is selected. So for R format, we have to put 1 here, so it selects this one. Let's see if I, correct, yes. Reg destination is 0. Now let's go to ALU source. So let me put a 0 here, 1 here. So for R format, reg destination is 1. ALU source is this one, and it selects with either the operand coming from the register file or coming from the immediate value. For R format, it should come from the register file. So it should come from here. So it means that the select should be 0. So ALU source will be 0. Branch is 0 because it is R format and it is not branch. Memread, if it is R format like add T0, T1, T2, then there is no memread. So memread will be 0. Mem to reg. What was mem to reg? Mem to reg was what do we want to update it? If it is R format, we want to update the register file using the ALU result. So this should be 0. This should be 0. ALU, mem to reg should be 0. ALU op, it depends on the function. It depends on the add, and, or something. I don't look at that. Memwrite. What would be the memwrite for our format? We don't have anything with memory. So memwrite is also 0. And what about regwrite? Regwrite would become active because our format will update the register file based on the ALU output. So you see, these are the control values which we have to find out for our format. You see, this is what we have found out. And again, you could do the same for load to see which will go, which I will give you maybe in the quiz or in the exam. That would be a good question for the exam. Okay, that's it. Okay, I stop here. Let's go to quiz. The quiz now is asking you from these control signals. So I will leave this on this page. So you need this maybe to answer some of the questions of the quiz. Okay. So the quiz is control signals, and the password is control. Small letters. Look at this. Oh, not this. You need that.